All right, so we're going to continue with the project management series in this and start getting into how some of the major tools for doing your management, and in particular system design. So a lot of what you're going to be doing in the system design is going to be very important uh, for your initial documents, the PDR, et cetera. So what we're discussing here with the system design is a very high level identification of your major processes, functional components, and their interfaces. Uh, you're going to derive what your system requirements are, and the system design gives a overview of the project. You're not necessarily going in and providing all of the definitions of exactly what's in your payload, your exact circuit diagrams, or which sensor that you're going to use for what. This is a high level discussion. It's where you start with your project development. It's important to understand what your components are, how these components communicate with each other, how you might modularize your project so that you can get this down into what are called discrete work packages, and also to identify things like critical interfaces and make certain that those critical interfaces are in fact well defined. So that's the purpose of what the system design is. You also use your system design for your initial cost, schedule, and resource estimates. Remember last time we talked that a project is limited in time and cost and other resources. Well, your system design is your first cut to try to identify how you're going to proceed within those limitations. Almost always in the system design, there are no implementation details, right? But as you go further and further into your system design, you may develop lower level subsystems which start looking like an implementation, but not exactly. So that's where we're going when we're talking about a system design. It's a high level thing. So here's the sort of steps that you do when you develop your system design. First, and the most important part, is to define your project goal and objectives. And a lot of these goal and objectives are derived out of your science background. So you have a particular investigation that you want to do. Well, you're going to have to do your research to look at the science behind it. What are the outstanding problems? What are the observations that have already been made? And your background. What is the type of thing that you're going to be looking at? From that, you obtain or derive your goal and objectives, and there can be both scientific and technical objectives at the same time. We'll talk about those in a minute. From those objectives and the goals, you derive your requirements, right? So requirements are things which are needed to achieve those objectives, right? So you derive from your science background to your objectives, and from your objectives to your requirements, okay? You don't start from, oh, I want to use this sensor, so therefore how do I justify it? That's called being backwards, right? We start from the science to the objectives to the requirements. Based upon those objectives and requirements, you now try to develop what your major system components are going to be. You already know what some of these are. You need power, so there's going to be a battery. You need to have some controller, so there's going to be a computer of some sort. There's probably some sensors. There's probably some storage thing. So you already know the major components that are going to be. And then how do these major components talk to each other? Is it serial? Is it networked? Is it some analog communication? Is it some physical structure between the two? Once you do that, now you'll do a refining of that subsystem of that system. You'll start defining the subsystems that make up. So your power subsystem will have individual pieces with it, voltage regulators, batteries, other kinds of things that might be. And again, your specific your interfaces between. And as you go through and define these components in your subsystem, there's going to be questions that will go back and force you to identify other requirements, like what should be the voltage on your battery, or other kinds of things like that. Then you also part of this is also to control your system interfaces. Make certain that everybody understands what it is that you're building, right? So those are the primary, that's the loop, the system design loop, if you will. So what's a goal and how is a goal different from an objective? So a goal specifies the overall purpose of the project. It defines what you wish to accomplish as a result. Very typically, I usually say that the goal should be a one-sentence a description of the who, what, where, and why of the project. Now, remember back when you were doing creative writing or courses or English courses, and they talk about the five reasons for a newspaper article. Well, this is sort of the same thing, except what you do is that you do this in one sentence. So a goal could be something like this payload measures the temperature profile from sea level to 100,000 feet in order to identify the location of the ozone layer. So there you go. So you got a what, you're measuring temperature, a where, altitude from ground level to 100,000 feet, and why, to identify where the ozone layer is. Okay, so that is a goal, right? There can be other goals that you would do too. All right, that's an overall statement. Objectives are discrete entities of items that you would accomplish during the project or resulting from the project. There are two different types of objectives. There are scientific objectives and there are technical objectives. So scientific objectives would be specific about accomplishing particular scientific goals. So a scientific objective would be for a goal that we've had, scientific objective would be to identify the temperature profile as a function of altitude, right? A technical objective would be to measure the temperature sufficient to identify the profile or something like that. So it goes into a more technical way as opposed to derived from your science. So you need to keep in mind that those two are different. The goal and the objectives then constrain and define the scope. This leads to defining your requirements, the actual statements of what is necessary in order to achieve those goals and objectives. Notice that I say that these are the things that are necessary, not that those are desired or possible, but things that are necessary. Requirements are also not implementations. Okay, a requirement is not necessarily to specify a particular kind of battery. That's an implementation. A requirement would be the power system shall provide 12 volts, shall provide 12 volts of power at 5 amps or 1 amp or whatever it is. That is a requirement. Doesn't tell you what the implementation is of it. So your requirements are listing the constraints imposed upon and resulting from the project. Right? These would be both scientific and technical objectives. All right, that would be reflected in these requirements. It is really important that you start from the beginning of your project and take the time to identify your requirements. In fact, the whole first part of the PDR document is devoted almost exclusively to goal, objectives, and the derived requirements. Until you actually get those three components identified and put down on paper and properly specified, it's almost impossible to go forward successfully with a project. So you need to spend the time right in the front getting those system requirements identified. Make certain that you start by initially developing your high-level scientific and technical requirements. So I provided you some examples of what those kinds of things would be. So using the science background that you develop, you know, what is the resolution and accuracy that you would need to accomplish your scientific objectives? If you are, since you're going to be flying on a balloon payload, there is going to be particular technical objectives and limitations that you're going to have. You're going to go into a vacuum type environment. So a technical requirement is that your payload has got to survive, 5 millibars of pressure. You're going to have, and all that implies, the 5 millibars of pressure means that things like convection and conduction isn't going to work very well. So you have to worry about, temperature control, maybe, or at least you have to worry about thermal design, right? So let's go through an example as to how this loop works. So the initial system design. So we start start with an initial design, and as I say, a lot of the system design goes hand in hand with the system requirements. Okay, so we know initially for almost any scientific measurement, you'll need a detector system and a power system and a data acquisition system and a data archive and a control system of some sort. And you also need something on the ground. You need a ground data system of some sort. And all of these functions have to have a set of requirements, right? You're going to have to obtain the requirements for your sensors, for your power system, et cetera. They're all going to have requirements on them as to what it is that you need. There's a very handy tool called the traceability matrix. All right, traceability matrix relates what your goal, objectives, requirements, and then eventually into your implementation. So there's different ways to do these things, but the traceability allows you to look at whether or not you have covered all of your requirements with a particular design, or if there are missing requirements. So one should be looking at trying to do that kind of traceability. Your major system interfaces need to be correctly identified and controlled. There's a real classic example. I think I talked to you guys about this before. The Mars Climate Observer in 1999 failed because the two systems that were using flight and ground control used two different units. And so that caused the climate orbiter to crash into Mars rather than to go into orbit. So you need to watch how your systems fit together. There are multiple interfaces. There's a mechanical interface. Obviously, you need to be able to mechanically put things together and make certain that they stay together. There's a power interface. So there's current flows, voltages, etc. Electronics, you got electronic signals, serial, analog, various things like that. Data, there's a content of your data systems. You will have data records. So what's the format and the content of that? Are you going to be using ASCII characters in your data? Are you going to be using compressed binary? You're going to have delimiters in that data. So you need to understand what that interface is going to be. Your flight and ground system are going to have to communicate with the data interface. Thermal, how does heat flow between different systems? And then your software. Your software is almost inevitably going to be composed of different routines or modules or subsystems, and all of those modules have to communicate with each other too. So these interfaces and the characteristics of each interface has to be identified and defined as well as your components. So here's a very high level, system level example. So this is a very, very early system level drawing for the high altitude student platform program that we've been flying for the last 15 years. And in this, for this project, we had wanted to be able to provide a high altitude, long duration, 15 hours flight for up to 8 student payloads, or 8 CubeSats, as we're calling it here, and be able to telemetry data down and provide each one of these payloads with power and power to run them, as well as telemetry to communicate. And so with that goal and those kinds of objectives, we can identify that, okay, we had 8 student payloads in here. Each of them is going to have a communication telemetry where there can be commands uplink. Notice the arrow is going into the CubeSat. And they can also downlink serial data. So there's an arrow coming down, all right? And we're also providing each of these guys with power, okay? So you see that there's power going into each one of these as well. And then in the flight instrument, there is some sort of a control unit. There is some sort of a unit that would archive the data. There is some sort of storage device. And there's a transmitter, auxiliary transmitter, that we would run to downlink data. And then there's also a balloon system control package that's in the flight that would send commands to the flight control system, and there would be uplink and downlink communication there. So that's a high level type thing. So here we've identified all the primary subsystems and their major interfaces, right? So now after you've sort of identified this high level design, now you want to go through and go one level down. So each of these major functions has multiple things that are going on inside of it, multiple activities, processes, modules, interfaces, etc. So for example, with this power system that I was talking about, there's some sort of a source of energy for the entire platform. And then there's supplies for each of these other units, the FCU, DAU, the DIS, the auxiliary transmitter, and the CubeSats. All right? And then each of these subsystems has an interface that you need to specify. What kind of interface do these subsystems have? How do these subsystems interface with other systems, and what is the content of that interface. And then there should always be a traceability matrix that would include these new subsystems as you develop this stuff. So here is now one level down, a subsystem. Remember in that previous slide, all right, the power system was a box and had a bunch of lines in it. Now we're going to define what's in that box a little bit more. So here's the power system subsystem. And in this power system, we know that we're going to have to supply the FCU. We know we're going to have to supply the DAU, the data archive unit, disk storage, and then 8 of the CubeSats. And we also have some sort of power source. But now we know that there's going to be a battery in here. We define what the main bus voltage is going to be, 28 volts. We know that each one of these supplies, we're going to want to control it. Not specified how it's going to be controlled yet. Just know that we want to control it. And we also want to sense what's going on in each one of these things. And we also know or define or set the requirements about what voltages come out of these different supplies. So for example, the CubeSats, there's going to be 8 of these, and these CubeSats supplies will provide a 5 volt and a 3.6 volt. The hard disk or the data storage will provide a 5 volt and a 12 volt, etc. So you see here that we're one level down, we provide more information. We are still not implementing anything. There is not one piece of hardware that is being identified here. It's still functional items, and it is still interfaces, what these interfaces are. Okay. So we can go one more level down, all right, and we can get closer to what the design specifics are. So let's focus on one of these supplies. So the FCU supply. So that FCU supply, we decide that the control is on off. So that's going to be a relay. So we know that there's going to have to be a relay in that FCU supply that allows us to turn that thing on and off. We know that to change the 28 volt bus battery, line voltage to that required 5 volt supply, there's going to have to be some kind of a DC to DC converter. We still don't know exactly what the model and make number is, but we know it's going to be a DC to DC converter. Then we know we want to monitor the voltage and current. So there's going to be inline sensors to be able to do that. These are things that we can do when we do the design. As you progress through this kind of thing, you'll now set requirements, on what is the exact capability of that DC to DC converter supposed to be. How much current should it be? What should be the temperature operating range? That's how this goes in a loop by loop. So as you go down further and further into your system design, you eventually migrate into a implementation. So here's what that next level would look like. So here is in fact that FCU. So we've identified that this battery is a lithium cell battery of 28 volts. That we have on this 28 volt bus, we have voltage and current sensing. Still haven't identified exactly what that is, but we know that that's going to be there. We've got a relay for on off. We have the DC to DC converter that takes that 28 volts and converts it back to 5. And we have voltage and current sensing in through here. We show that there's 2 lines coming out for that. And so, and likewise for the CubeSat supply and for the data archive supply and for the DAU. So those are the things that you see. Now notice here. Now this is an interesting one. So notice here that in a previous design we had the DAU hard drive. That's what HD stands for in this case. There was a box which had 12 volts and 5 volts coming out. Now, what we've got here is that we decided in our design that we're going to group the 5-volt together for the DAU and have a separate 12-volt. So we'll run the 5 volts on one relay and the 12 volts on another relay in here. And so we'll do that. So just simply because you identify at one level of your subsystem, it doesn't mean that you have to keep to that. You need to make your design that is logical. Now, these are really close to implementations at this point. In fact, the next step beyond this would probably be full hardware and interface specifications. Okay, so you get what we're going with this stuff. You're working down the line in a very systematic and progressive level as you go through another level of your system design. Other kinds of requirements need to be specified and answered. You'll have questions that come up for these components, and those questions get answered with your requirements that you go. And that's how you progress through this. At the PDR level, this is probably where you're going to be. All right. Remember that at a PDR, you are doing mostly a paper study. You are not necessarily doing anything with resistors or capacitors or anything like that. You are doing a system design. And this is probably about as low level of your system design that you need to go in the PDR. Maybe one level lower, but probably not that much. All right. It's very important that you pay attention to your interfaces. So when you're working on a project, not everybody is going to be doing everything, okay? Very likely you'll have one person who will be specializing in the electronics, another person who will be emphasizing software. And so you need to make certain that everybody is communicating. So you can't have the electronics guy go and change the hardware interface from a serial to from a straight serial to an I2C or something like that, and then expect software to understand that implicitly and say, oh yeah, that's fine, and go through and just implement it. Software is going to go through whatever was told to him previously, and so he's busily implementing an RS-232 type interface while electronics is building an I2C bus. And the result is that it probably is not going to work once they put it together. So you need to be able to specify those interfaces and have that written down. Many times this is done with what's called an ICD, or an interface control document. So written description of that interface. And it allows people who are working more or less independently to be able to understand what they are developing, right? So that's an important thing to keep in mind. Not all interfaces need to be controlled, but the critical ones should be. All right. So that's all that I got there on the system.